A small object of mass m kilograms is placed on a rough horizontal disk at the distance of 0.07 meters from the center. When the disk is rotated at a rate of 1.5 revolutions per second, the object is on the point of slipping. Calculate the coefficient of friction between the disk and the object. To understand how to do this question, first of all we have to understand what's meant by the coefficient of friction between two surfaces, and it's going to be a different value depending on the surfaces in question. For example, how does it work? Well, suppose I've got a large box sitting on a desk, for example, and I wish to push the box across the desk, and I push the box with a force of 10 newtons and the box doesn't move. This means the force of friction acting in the opposite direction on the box is also 10 newtons, and we say the forces on the box are balanced by Newton's first law. Then we come across with a larger force, 20 newtons, but the box is still not budging. It means the force of friction against the box is 20 newtons and the forces are balanced. But suppose I come across with a 25 newton force and the box is on the verge of slipping. Now at this point I can define my coefficient of friction at the point where the box is just about to slip, and I can say the force of friction is equal to mu, the coefficient of friction between our two surfaces, times n, the normal force acting on the block, which is just going to be the weight of the block in this context because it's moving horizontally. And that's what's meant by the coefficient of friction. So to our problem then, we have a box on a disc, and the box is going round and round with the disc, and we're asked to find out what is the coefficient of friction between the box and the disc given the box falls off at 1.5 revolutions per second. Well, this is a force problem and we have to use Newton's laws of motion. What do we know about that? Well, the first thing we're told that the box is going round. Well, if the box is going round and round and round, it's continually changing direction. Therefore there must be an unbalanced force acting on it. And then we use Newton's second law. And Newton's second law says that unbalanced force has to be equal to m times a. But since it's circular motion, we know that the acceleration has to be equal to v squared over r. And that is the unbalanced force acting on the box as it's going around the circle, mv squared over r, or using rotational quantities, m r omega squared. Now, how does the force arise? Well, when the box goes around and round and round, it's pushing outwardly on the disc. Therefore, by Newton's third law, the disc will push inwardly on the box with the exact same magnitude of force. Of course, the disc pushing back on the box inwardly is the frictional force, but that has to be equal to mv squared over r, as we've already stated. So the frictional force is equal to mv squared over r. Now, the frictional force will always be equal to mv squared over r, but when it comes to the point of slipping, when it's about to leave the curve or leave the disc, mv squared over r, and at this point only is equal to mu times n. So our problem reduces to this. Mu n is equal to mv squared over r, or mu n is equal to m r omega squared. Put our values in, solve it for our coefficient of friction.